Hello, everyone. As said, yeah, I'm Abigail Frost. I'm a postdoctoral research associate at KU Leuven, and I like to look at massive forming stellar systems and also massive multiple systems across their lifetime. And today I'm going to talk to you about a couple of projects that I've been working on recently, where I've been looking at massive binary systems which potentially have recently gone through an interaction. Ooh. Okay, so Emma Bourdieu, who gave a talk on Monday, already touched on why massive stars are important, but I just wanted to reiterate that these stars are very, very influential, not only from their kind of local scales, so where they can affect the distribution of material in the star-forming regions where they were born, but also up to very large scales, affecting the topology of the galactic superwind, for example, creating supernovae, and creating gravitational waves, and also very importantly, enriching the ISM. And in this little periodic table that you can see here, anything in yellow and purple is linked to the behavior and evolution of massive stars. And this influence that massive stars has is uniquely related to their multiplicity. We know that most OB stars, around over 90%, are expected to exist in at least a binary system or a higher order multiple system. And furthermore, a large proportion of these systems can also be expected to interact. Well, around 70% of them are expected to interact in some form throughout their life. And of course, when these interactions happen, there's an exchange of mass, there's an exchange of angular momentum, and it can change the chemical composition of the stars involved, and therefore this can affect all of these, the feedback and the final fates of these stars, which have these effects on small to large scales. So here's a very simplified kind of cartoon showing the evolution of massive stars from the star-forming region through the massive young stellar object phase at the pre-main sequence, which Evgenia Kumpia gave a really nice overview about yesterday as well. And moving on to the main sequence of the very young systems that Emma Bourdieu talked about yesterday. But today I'm going to focus on this stage here, where we can look at binary systems that have recently gone through an interaction to work out what exactly happened and what has been affected due to these binary reactions. So there's two sources that I want to mention today. And the first is HD 148937, which is a pretty cool system because it seems to have one magnetic star. So to give a bit of background on this system, HD 148937 is classified as an OF P star, which is a very rare subset of O-type stars, of the most massive stars. This kind of class of star was defined by Walborn in 1972, and they're characterized by the presence of these spectral lines in their spectra, which are associated with the magnetic properties of the stars. HD 148937 specifically was directly determined to be a magnetic star in two studies around 10 years ago, and it's been known to have a longitudinal B field of around 300 Gauss. Surrounding the system of the stellar system, we also have a very complex nebula system, which has been determined to have multiple components. For example, there's a bipolar component, a helical-shaped ejector component, an ellipsoidal windblown shell, and also an ionized sphere that contains CNO processed elements. And also fairly recently, the star was confirmed as a binary system during the Southern Massive Stars at High Angular Resolution survey, which is done using interferometry data and also some sparse aperture masking data. And also this source was confirmed to be a spectroscopic binary as well, using a lot of multi-epoch data, and that work was done by Greg Wade in 2019. So we decided to look at this system with interferometry, specifically gravity observations with the VLTI. And like many other people, we used Antoine Ménon's code PM Poiret to look at, or to perform the geometrical modeling of our data sets. So here you can see the UV coverage of our observations. We had two epochs of gravity data, one taken in June 2016 and one taken in September 2016. And you can see an example of the observables here. So in the bottom right, you can see the normalized flux, and here we can see a very clear bracket gamma line emission. And we can also see the evidence of this line in the closure phases, differential phases, and the visibilities as well. And by fitting these two data sets, essentially we found that well, one nice thing that you can do with Poiret is you can attach a spectral line to individual components of your geometrical model. So you can have, for example, an emission line in one star, an emission line in both stars, and by varying running, a lot of different kinds of models, we're able to determine that the best fit to the data was obtained if this bracket gamma line emission is coming solely from the brighter star in the system, the brighter and more luminous star in the system, so the primary star here. And that's just quite interesting because that implies that the magnetic signatures that we're seeing from the system are also associated with only one star in the system, because bracket gamma can be a signature of a magnetically confined wind. And this is interesting because if you had two stars forming out of the same kind of area, you wouldn't expect one to have magnetic field lines, if it was kind of a fossil field that led into the formation of these two stars. And that implies that maybe something has happened to the primary star in this system to give it this magnetic field while leaving its secondary star without one. So we combined our gravity data with extra data from Pioneer over some other epochs. And we also combined it with the spectroscopic data that was used in 2019 to determine that the source was a spectroscopic binary. And by using the spectroscopic and interferometric orbital solution finder, which is a nice orbital fitting tool designed by PhD student Matthias Rabi at KU Leuven, we were able to converge an orbital solution for the data, which you can see here. It's a very long period of 9,900 days, which is around 20-something years, I think. Fairly eccentric orbit as well. And you can see the other parameters here that I'm not going to go into in too much detail here. And essentially what we did with the, once we had this kind of astrometric data and a confirmed orbit, is we wanted to go back and see if we could determine the parameters of the individual stars. To do this, we did a technique known as spectral disentangling of the spectra, again from that Wade study. And essentially this gave us three competing models for the kind of nature of the stars in the system. And two of these scenarios are quite interesting because they basically imply that an interaction has happened within these sources. So in one case where the primary, is now appears much younger than the secondary star, that implies that perhaps a merger could have created this primary star, and that the system was originally a hierarchical triple. And we've done some hydrodynamical modeling with Fabian Schneider at Heidelberg, and he's found that indeed this rejuvenation could be created by a merger of two other stars, which then created this primary. And in another scenario we have where actually the secondary appears to look a bit younger, could have been also explained if a different kind of interaction had taken place. And this is where we've had a kind of flyby event between the two stars, and this has stripped a lot of material from one of the stars. And we're currently trying to study the system. This was ongoing work, preliminary results, to determine which of these scenarios is more likely. So now I'd like to talk about a different system. This system is HR6819. Again, this seems to be a system which has potentially recently gone through a binary interaction. So HR6819 is a B-star system. It's around 350 parsecs away. It's quite bright in the visible, and it's been known to be a binary for a long time, since around the 60s. And it's also an interesting system because it shows the emission signatures of a classical BE star. And we already heard a little bit about BE stars today from the nice invited talk we just had. And essentially one prime channel, we think, for causing these BE stars, which are categorized by their rapid rotation, which is leading to the formation of a decretion disk about their equator, is that potentially a binary interaction could have caused this. So the idea is that you have two main sequence stars, one has expanded, Roche overflow has occurred, and this transfer of material has spun up that star, giving it a kind of the high rotational speeds that we see, and also leaving the donor star with a kind of looking a bit strange and looking stripped. And HR6819 gained a lot of attention 2 years ago in 2020 because it was claimed to be a system containing the nearest black hole to Earth. And this was done using Ferrous spectra. And essentially what they determined by looking at the variation of their spectral lines, that they thought that the BE star was on a slow, wide orbit, and that there was a B star in a 40-day orbit with an unseen companion. And given their estimate of the B star size of around 5 solar masses, they determined that this unseen companion was 4 solar masses and therefore had to be a stellar mass black hole. However, this theory was kind of met with some rebuttal from two other studies, in particular El Badri 2020 and Bodensteiner 2020, who proposed an alternate scenario. And essentially they found by reanalyzing the spectra that no black hole was needed, and you can instead explain the spectra that we're seeing, which you can see here, by having a BE star in that 40-day orbit, but with a stripped BE star, so a slightly different object. And so essentially we had two commuting scenarios from the spectral data. And if it was the triple system with a black hole, we'd expect a bright source and 10 or 100 milliarc second scales, and only one bright source in milliarc second scales. And if the system was a binary, we'd expect no bright star at those 100 milliarc second scales and two bright sources in milliarc second scales. And so we needed new data to determine the difference here. And so I'm going to kind of take you on a journey of like the fitting process that we did to determine the true nature of the source. So again, we were using gravity VLTI data and fitting this with Poirot. And essentially what we found was that in the, we again have some bracket gamma emission here, but you can see there's actually quite a nice double peak feature here. And we also had interesting kind of artifact in our closure phase data because we had gravity data taken in two polarization planes and the signal would flip between the two planes. And so because this kind of confused the fitting of it, we relied a lot on the differential phases to unveil the nature of the source. Now, this is the fit I'm showing you here in red is actually just for a very simple model. This is just for a 2-point source model. And you can see that that is not very well recreating this double peak feature and also not very well fitting the peaks in the differential phases. And so this indicated to us, because we have this double peak feature, that we have a disk and that there is kind of some rotating structure here. And but here is the model that you can see for the simple point source model. And the key point here is that the two stars are separated by 1 milliarc second. And so because we had this kind of suggestion of a rotating structure and perhaps a disk, we decided to try and fit a Keplerian disk model within the code to the data. We had some troubles converging. I think this is because technically these VLTI baselines were not meant to be resolving, or we shouldn't be able to resolve these kind of BE style disks because they're only kind of stellar radii in size. And so in order to assist the code, we kind of broke down a disk into a toy model. And we have, so the redshift component, the blue shift component, and kind of a neutral continuum component for this star, the brighter star, which was showing the evidence of the bracket gamma. And we still have the secondary star as well here. And by using this and the kind of separations of these components to feed into a first guess for the disk radii, for example, we were able to converge on a disk model, which you can see here. And so here you can see the disk in two different velocity channels. And we can see that we have a disk elongated in the direction of the orbit of the system. And this provided a much, much better fit to the data with this double peak profile now very nicely recreated, and also the shapes of the differential phases and even some very subtle features in the visibilities as well. And so combining this interferometric data with additional Muse data, which checked the wider region, we're able to determine from the Muse data that there's no bright companion at the kind of 100 milliarc second scales. And from the gravity data, we know we have two bright sources at 1 milliarc second scales. And so we can rule out the triple scenario and essentially determine that, in fact, we think HR6819 is a binary with a 1 milliarc second separation. And that furthermore, the brighter star in the system, which shows the bracket gamma emission, also appears to be a BE disk. And so basically interferometry was a key player in determining the true nature of this system. And so I hope I've convinced you in my talk that spectro-interferometric data in particular can tell us a lot of interesting things about the properties of our sources and whether they've potentially gone through an interaction. I'm really looking forward to the future of this by continued studies with Gravity Plus and also Spica when it comes online. So thank you very much.
Very much again, two very interesting binary systems. Are there any questions to Abigail? Let's go ahead.
Hi, Gail Schaefer from the Chair Array. So in the toy model for the binary, the disk around the BE star, how well can you constrain the orientation of that disk from the interferometry?
Yeah, so the orientation essentially came from, it was very similar to that first guess we did by breaking it down into the toy model. But yeah, it was fairly well constrained and the errors were decent. So yeah, we were pretty happy with the orientation we got. But as I said, yeah, this is all basically based on the fitting to the normalized fluxes rather than anything else, because obviously this disk is not very well resolved. So we're relying on the normalized flux fit and the differential phase fit to constrain this rather than the visibilities. So yeah.
I see no online questions. Anything else from the audience? I have a quick question. So you basically studied the bracket gamma line for both systems. And I was wondering if there are any hydrogen lines or other lines of other elements that would help us understand these systems better.
We didn't notice any significant features in our K-band spectrum, at least, but potentially looking at a high resolution spectroscopy at different wavelengths in the optical could reveal some more interesting behavior. And we know that HD 148937 has a plethora of interesting lines because it's this strange magnetic system. So, but within our gravity spectrum, it's mostly bracket gamma that we could rely on. So.
Thank you very much. Let's thank Abigail again.